So, um, a quick overview is that today I'll be going over the introduction and history, data representation, operations on um, data, and the rest of the algorithms will be touched upon in the second session. Okay, so basically, quantum computing dates back to the 1980s, right? When physicists such as Richard Feynman and David Deutsch proposed the concept of using quantum mechanics to perform computations. Classical computers struggle with certain problems that quantum systems can effectively or efficiently solve, like simulating quantum physics. The notion of quantum algorithms arose from this, promising to revolutionize fields such as cryptography, optimization, and drug discovery. Quantum algorithms harness quantum principles like superposition and entanglement to process information in fundamentally different ways compared to classical algorithms, offering exponential speed up for specific problem sets. Data representation in quantum computing. Data is represented using quantum bits or qubits, which differ from classical bits by allowing superposition. While a classical bit can either be 0 or 1, a qubit can exist in both states simultaneously, as many of us know, enabling quantum computers to explore multiple possibilities in parallel. Quantum data is manipulated using quantum gates that perform operations in qubits, such as flipping their state or entangling them with others. This parallelism allows quantum algorithms to process data at a vastly faster rate than classical counterparts in certain applications, such as solving large, complex systems of equations or factoring large numbers. The operations, well, quantum operations involve manipulating qubits using quantum gates, which apply transformations that can change the qubit state. Common quantum gates include Hadamard gate, which creates superposition, and the C0 gate, which entangles qubits. These operations are reversible and form the foundation of creating quantum circuits. Quantum operations exploit quantum phenomena like interference, which different quantum states can cancel each other out or reinforce one another, enhancing the probability of correct outcomes. The power of quantum operations lies in their ability to handle complex calculations in parallel, accelerating certain computational tasks beyond the reach of classical computing. So it's a confluence of deep ideas, right? The quantum information processing. Quantum computing represents a thin synthesis of ideas from multiple disciplines, each contributing to its development. Physics forms the foundation by providing the principles of quantum mechanics, such as superposition and entanglement, which are essential for quantum algorithms. Mathematics offers entanglement, which are essential, the abstract framework to model and analyze quantum processes, while computer science provides the algorithms and computing models that leverage quantum properties for problem solving. Chemistry benefits from quantum computing's potential to model molecular interactions with high precision, a task infeasible for classical computers. Additionally, fields like material science and engineering are crucial in developing practical quantum hardware. Quantum computers. Quantum information processing is a rapidly advancing field with research focused on several key ideas and several key areas. One major front is the construction of quantum computers. and quantum sources, which are essential for realizing the potential of quantum computing. There is also significant work on developing quantum information theory, which provides the mathematical foundations for understanding quantum states, as well as methods for error correction, which are crucial for ensuring reliable computation in noisy quantum environments. Additionally, research is advancing in quantum algorithms and communication protocols, with applications such as cryptography and quantum teleportation offering exciting possibilities for future innovations. A quantum computer, as we were talking about earlier, performs calculations based on the principles of quantum mechanics. Quantum mechanics is the branch of physics that explains the behavior of matter and energy at the smallest scales, such as atoms and subatomic particles. Unlike classical computers, which rely on bits that are either 0 or 1, quantum computers use quantum bits or qubits. These qubits can represent 0 and 1 simultaneously due to superposition, enabling quantum computers to perform many calculations in parallel. Additionally, quantum entanglement allows qubits to be linked, enabling faster and more efficient problem solving. This fundamentally different approach allows quantum computers to potentially solve problems that are intractable for classical computers, such as simulating complex molecular interactions or factoring large numbers, with applications in fields like cryptography, optimization, and drug discovery. Quantum computing has evolved significantly with pivotal contributions from leading figures. In 1982, Richard Feynman famously remarked that nobody fully understands quantum mechanics. Yet he proposed a revolutionary idea, machines based on quantum mechanics instead of classical physics. In 1985, David Deutsch introduced the concept of quantum Turing machine, showing that quantum circuits can be universal, laying the groundwork for quantum computation. In 1994, Peter Shor developed a quantum algorithm capable of factoring large numbers in polynomial time, marking a major breakthrough. In 1997, Love Grover introduced a quantum search algorithm with complexity, demonstrating quantum computers' potential for faster problem solving than classical methods. The pictures here depict computing or classical computing using bits to represent information where each bit is either 0 or 1, forming the foundation of a traditional computation. A classical Shannon bit is decisive, meaning it can only exist in one state at a time, either 0 or 1. This simplicity makes classical bits easy to store, transfer, and manipulate. Additionally, classical bits are easily copied, meaning that once a bit is created, it can be replicated without restrictions. For example, a copying machine can generate an identical bit from the original. This is in contrast to quantum bits or qubits, which follow different principles and cannot be copied in the same manner due to the no cloning theorem. Unlike classical bits, quantum bits or qubits have the unique ability to exist in a superposition of both 0 and 1 simultaneously. This characteristic is often referred to as being indecisive, as a qubit is not strictly one state or the other, but a combination of both until measured. This feature of qubits is fundamental to quantum computing and allows for parallel computation, significantly enhancing the processing power. One common representation of a qubit is through a spin of 1/2 particle, where the spin up state is denoted as 1, and the spin down state is denoted as 0, reflecting the quantum mechanical properties of subatomic particles. Quantum states are the foundation of quantum computing, and their manipulation is key to the development of quantum algorithms. Several quantum phenomena govern these states. 1, superposition allows qubits to exist in multiple states at once, enabling parallel computation. 2, entanglement links qubits in such a way that the state of one qubit is dependent on the state of another, even across large distances. Unitary evolution refers to the continuous transformation of quantum states through quantum gates, preserving their overall probability. 4, measurement collapses a quantum state in a definitive state, 0 or 1, which is then read out as the output of quantum algorithm. These quantum phenomena work together to form the basis for developing powerful quantum algorithms capable of solving problems exponentially faster than classical methods. In quantum computing, a qubit represents a single bit of data and can exist in 2 distinct states, 0 and 1. These states correspond to the 2 basic values of the classical bit, but in quantum mechanics, these states can be described by quantum wave functions. A physical implementation of a qubit might utilize the energy levels of an atom. Specifically, the ground state of an atom would represent 0, while an excited state will represent 1. These transition between the ground and exciting states is typically achieved by applying a light pulse of specific frequency, causing the atom's electron to jump between the 2 energy levels, thus encoding the qubit's information. A single qubit can be placed into a superposition of 2 basic quantum states, 0 and 1, through the addition of state vectors. This superposition is represented by the equation here. And these are complex numbers. And the magnitudes of these coefficients satisfy the normalization condition, as explained here. A qubit is in superposition simultaneously in both the 0 and 1 states, which means that before measurement, the qubit exists in a combination of these 2 states. Once measured, the qubit will collapse into one of the 2 states, with probabilities determined by the square of the magnitudes of the alphas. Consider a 3-bit quantum register where each qubit can be in a superposition of states of 0 and 1. In such a case, the total state of the system is a superposition of all possible combinations of 3 bits. If the superposition is equally weighted, the state is expressed as the equation depicts. This means that before measurement, each possible combination of 3 bits is represented with an equal probability. The system exists simultaneously in all states. Upon measurement, the system collapses into one of the 8 possible states with the corresponding probability based on the coefficients of the superposition. In quantum computing, a qubit is mathematically represented as a vector in 2-dimensional complex vector space, also known as a Hilbert space. This space allows for the representation of a quantum states as linear combinations of basic states. Dirac's notation is commonly used to describe qubit states. The ket notation, written as it is here, represents a column vector, while the broadside notation, written as the slide represents here, is also represented the conjugate transpose, or the row vector of the ket. The bra is also referred to as the dual vector, which involves transposing and taking the complex conjugate of the original Ket vector. Realizations of qubits include physical implementations such as nuclear spins, positive or negative, photon polarization, left or right, and electron states, ground or excited. A classical bit can only be in one of two distinct states, 0 or 1. Measurement of a bit does not alter its state. It will remain in its value until intentionally changed. In contrast, a qubit can exist in a superposition of both states 0 and 1 simultaneously, as represented by the equation here. These are complex numbers, and their magnitude satisfies the normalization conditions. When a qubit is measured, it collapses into one of its basis states. The probability of finding the qubit in state 0 is given by the bottom equation. Unlike classical bits, qubits can be in a linear combination of their states until observed. The box sphere is a geometric representation of a qubit's state in a superposition. A qubit is represented as a vector connecting the center of the block sphere to a point on its surface. The position of the point on the sphere's surface corresponds to the state of the qubit, where the two basis states 0 and 1 are represented. Sphere. The two probability amplitudes of the qubit, A0 and A1, or alpha 0, alpha 1, can be represented using Euler angles, which describe sphere, its position in space, allowing the representation of complex superpositions of states. In quantum computing, a qubit exists in superposition of states represented as points on the block sphere, part B of the image. Before measurement, the qubit can be in any state on the surface of the sphere, corresponding to the combination of basis states 0 and 1, as shown in the superposition states. Upon measurement, the qubit collapses to one of the two basis states, 0 or 1. The probability of observing the qubit in either state is determined by the probability of amplitudes, which are squared magnitudes of the respective coefficients in the superposition. After the measurement, the qubit state is fixed in one of these two states. You can see the figure illustrates that change in state from a superposition to a definitive state post-measurement. Two qubits are represented as vectors in a four-dimensional Hilbert space, where the states are written as so. Corresponding to 2-bit states. These states form the basis vectors for the 2-qubit system. When measuring a pair of qubits, the system collapses into one of these four basis states with probabilities determined by the squared magnitudes of the corresponding coefficients. The probabilities of finding the system in each of the four states are given by the probability equation, as you can see below here, respectively. Before measurement, the state of a system consisting of 2 qubits is uncertain. This uncertainty is represented by a superposition of the four possible states, 0, 1, 10, and 11, with each state having an associated probability amplitude. The probabilities for each state are determined by the squared magnitudes of the coefficients as described in the previous equation. After the qubits are measured, the state collapses to one of the four possible outcomes, and the system becomes certain. The qubit system will then be in a definite state, much like a classical two-bit system where the state is always known upon measurement. If we observe the first qubit of a two-qubit system, we cannot determine the state of the second qubit, leaving the system in an uncertain state. This is because the second qubit remains in a superposition of states as it was not measured. The measurement of the first qubit can be described probabilistically. The first qubit can be in a state 0 with probability. The first qubit can be in a state of 1 with probability, as denoted in the slide. In this case, the state of the second qubit remains interdeterminate, and the system is only partially observed. Thus, we can make conclusions about the state of the first qubit, but the second qubit's state is still unknown. In quantum computing, an n-qubit register can represent the numbers as depicted here, simultaneously due to the principle of superposition. This means that a quantum system can encode a large number of possible states at once, making it appear as if it can process many possibilities in parallel. However, as impressive as this sounds, it's not entirely true. When attempting to retrieve the values from a superposition, the state of the qubits collapses randomly to just one of the original values. For example, in this equation, the coefficients represent the probability amplitudes. When the qubit is measured, the superposition collapses, and the qubit will be found in state 0 with probability alpha squared, or in the state 1 with probability alpha 1 squared. Entanglement is a fundamental concept in quantum mechanics, originally coined by Schrödinger from the German term Verschränkung. It refers to the phenomenon where two quantum particles become intertwined in such a way that the state of one particle is directly related to the state of the other, no matter the distance between them. An entangled pair is a single quantum system in superposition of possible states, where the individual particles' states are unknown but correlated in opposite states. The state property of entanglement is the measurement of one particle immediately influences the state of the other. This is famously known as the spooky action at the distance term, used by Einstein to describe this instantaneous connection between particles. For example, imagine two qubits, each in a superposition of state 0 plus 1. These qubits can be entangled so that measuring the state of one qubit will always reveal the state of the other qubit, no matter how far they are apart. This slide covers the classical logic gates used in computing, which are essential in both classical and quantum systems for manipulating bits. These slides will be shared later so that you guys can take a look at these logic gates. But in essence, these gates are fundamental to all classic logic circuits and can be adapted for quantum logic circuits with quantum gates. Though quantum gates operate on quantum bits, qubits, and can exploit quantum properties like superposition and entanglement. In classical computing, gates like the AND gate can be used to perform logical operations. However, due to the principle of quantum mechanics, the destruction of information in classical gates can lead to the loss of superposition state of qubits. When information is lost in a gate, it causes heat to be evolved, which in turn destroys the delicate superposition of quantum states. For example, consider the AND gate with inputs A and B. The output is C as shown in the truth table on the right. As you can see, in 3 of these cases, information is destroyed. This loss of information makes classical logic gates like AND unsuitable for quantum computing. Instead, quantum gates must be used as they are reversible and preserve quantum information. Quantum gates are similar to classical gates in that they manipulate qubits, but they differ in an important way. Quantum gates do not produce a degenerate output. This means that for any output state, the original input state can be uniquely derived. This property is essential for quantum computing as it ensures that the operation is reversible. Reversibility is a key feature of quantum gates, and it is necessary for performing deterministic computations on a quantum computer. According to Charles Bennett's work in 1973, it has been shown that any deterministic computation can be made reversible, which is crucial for the functionality of quantum systems. This contrasts with classical gates where information loss can occur, making reversibility impossible in some cases. The Hadamard gate is one of the simplest quantum gates, operating on a single qubit. It is often referred to as the square root of the NOT gate. The Hadamard gate is primarily used to create superposition states from the computational basis states 0 and 1. When applied to the state 0, it transforms the qubit into the state, which is an equal superposition of 0 and 1. The Hadamard gate, when applied to 1, transforms to the qubit into a superposition of states of 0 and 1 with equal probability, specifically in the state as depicted in the picture. This gate is crucial for quantum computing because it allows for the creation of quantum superpositions, which are foundational for quantum algorithms. Note here that 2 Hadamard gates applied in succession can be used to function as a NOT gate, flipping the state of the qubit. The C-NOT gate, or the controlled NOT gate, operates on 2 qubits and is used to perform a conditional flip, NOT operation, on the target qubit. It uses a control qubit to determine whether to invert the state of the target qubit. Specifically, if the control qubit B is in the state 1, the target qubit A is flipped or inverted. If the control qubit B is in the state of 0, the target qubit A remains unchanged. The C-NOT gate functions similarly to the XOR gate, but with some additional information to ensure that it is reversible, which is essential for quantum computation. In quantum computing, we can create a reversible logic circuit to calculate multiplication by 2 using controlled NOT or C-NOT gates arranged in a specific manner. The logic operations is as follows: input, carry bit, and ones bit. The carry bit can either be 0 or 1, and the ones bit can be 0 or 1. From the output's perspective, the output will also contain a carry bit and a ones bit. When the carry bit is 0 and the ones bit is 0, the output is 0, 0. When the carry bit is 0 and the ones bit is 1, the output is respectively 1 and 0. This setup uses a quantum operation with Hadamard gates, H and C-NOT gates. The Hadamard gate is applied to create superpositions, and the C0 gates are used to flip the state of the carry and the ones bits in such a way that it simulates multiplying the number by 2. The controlled NOT gate, also known as a Toffoli gate, operates on 3 qubits, 1 target qubit and 2 control qubits. The CCN gate inverts the target qubit only if both control qubits are in the state of 1. If either control qubit is in the state of 0, the target qubit remains unchanged. A here is the target, the qubit whose state may be inverted. B here, control 1, the first control qubit, and C, respectively, the second control qubit. This gate is useful in quantum circuits where conditional inversion based on multiple control qubits is needed. It is reversible and forms an important part of quantum error correction and classical reversible computation and quantum algorithms. The controlled NOT gate has been proven to be a universal reversible logic gate. This is because it can be used to simulate the NAND gate, which is fundamental in classical logic for performing logic operations. By applying the CCN gate, the system behaves in such a way that is equivalent to the NAND gate operation when the target qubit is 1. In terms of the functionality, when both controls qubits B and C are in the state of 1, the target qubit A is flipped. This behavior mirrors the NAND gate's operation. The NAND gate outputs 0 when both inputs are 1 and the outputs are 1 in all other cases. The truth table for this operation is already shown here. When A target is 0, the output is unaffected by the control qubits. When A target is 1, the output is the result of the NAND operation between B and C. This universality property is crucial for the construction of quantum circuits, as it allows quantum systems to simulate classical logic operations in a reversible manner, which is essential for quantum computing. Classical and quantum systems. Well, in both classical and quantum systems, the state of a system is described using probabilistic values, but the representation and the behavior of those states differ significantly. Classical systems have states that are represented as probabilistic distributions, where each state has a probability, and the sum of the probability is always equal to 1, or in most cases. The classical system can be represented as a vector with probabilities associated with each possible state. For example, in a 3-bit system, the states can be P0, 1, 10, 1, 11, while ensuring this total probability is 1. Quantum systems. In quantum mechanics, the state of the system is represented by complex number associated with each possible state. Quantum states are described by using Dirac notation. The expression represents a superposition of quantum states where each state is denoted by a Dirac notation. The coefficients of these states are represented by complex numbers. The difference between the two systems lies in probabilistic nature of classical system with real probabilities versus the complex superposition in quantum systems with complex probability amplitudes. Dirac notation is a standard method used to represent quantum states and the operations in quantum mechanics. It's widely used in quantum computing to describe states and the operations on qubits. This is a breakdown. The Ket notation represents psi, always denotes a column vector. For example, the state 0 is represented as a column vector, 1, 0. Bra psi denotes a row vector that is the conjugate transpose of the Ket vector. The elements of the bra are the complex conjugates of the coefficients in the corresponding Ket vector. The bracket notation represents the inner product between the two quantum states here. And it's referring to the inner product between the bra and the Ket. This operation calculates the overlap or similarity between the two quantum states, as depicted here in this slide. In quantum computing, the basic operations on qubits can be described through the following steps. 1, initialize the qubit. Start by setting the qubit to one of the basis states, typically Ket 0 or Ket 1. The states are represented as column vectors. 2, apply a unitary operation. A unitary operation is a linear transformation that preserves the norm of the state vector, and mathematically represented as so here. It refers to a unitary operator, a mathematical transformation, which denotes the conjugate transpose, also called the Hermitian conjugate of the operator. I is the identity of the matrix here. So the unitary operations. Rotation. This operation rotates the qubit by an angle in the block sphere. Not gate or a bit flip. This is represented by the poly X matrix. Phase flip. This operation is represented by the poly Z matrix. More examples of unitary operations which are closely related to the rotations in quantum mechanics can be depicted here in this slide. Number 1, Hadamard gate. The Hadamard gate is one of the most fundamental quantum gates. It applies a rotation that transforms a basis state into a superposition of basis states. It is represented by the following matrix, as you can see. Number 2, geometrical interpretation. The Hadamard gate acts as a reflection about the line on the Bloch sphere, which is a rotation operation in the state space. In summary, the Hadamard gate is crucial in quantum algorithms for creating superpositions of quantum states. The result of applying the Hadamard gate to a state is a rotation that enables quantum parallelism, one of the key features of quantum computing. Standard measurements. After preparing a quantum state, we can perform a measurement in the standard computational basis. The state collapses to either Ket 0 or Ket 1 based on the probabilities. This collapse of a quantum state upon measurement is one of the key features of quantum mechanics. The state of the qubit before measurement is a superposition, but after measurement, it becomes a definite state 0 or 1. The quantum state vector can be represented by the Bloch sphere. The components alpha and beta correspond to the coordinates on the sphere. It should be noted here that there are many other types of quantum operations, but they can all be expressed in terms of basic operations like rotations, measurements, and unitary transformations, which can simulate various quantum gates and states. A little bit more info. Quantum computer simulation, well, actual quantum computer hardware is currently limited to research labs. Quantum algorithms can be created, developed, and tested through simulations on existing classical computer systems. A qubit definition. A quantum bit or qubit is the fundamental unit of quantum computing. Unlike classical bits that can only be one of two states, 0 or 1, qubits can also exist in coherent superposition of these states, which is a combination of 0 and 1 at the same time. Quantum algorithm purpose. Quantum algorithms are designed to provide an exponential speedup over classical algorithms when solving certain types of problems. These algorithms leverage quantum mechanics to explore many possible solutions simultaneously. Quantum algorithm characteristics. A quantum algorithm consists of a series of instructions for quantum computer. However, unlike classical algorithms, the results of quantum algorithms cannot always be guaranteed due to the probabilistic nature of quantum measurements. This image, as you can see here, is a quantum algorithm zoo that categorizes various quantum algorithms based on their characteristics and speedups. Exponential speedup, we've got the Deutsch Josa, Simon's, Shor's, quantum hidden subgroup algorithms. 2, quadratic speedup, Grover's amplitude amplification algorithms. 3, quantum simulation of quantum systems. 4, non-classical behavior includes quantum random walks. And 5, which are a list of other algorithms like Jones polynomial algorithm, trace estimation, adiabatic algorithms, and anything that is the new and upcoming. The algorithms mentioned represent different computational paradigms in quantum computing, each offering different benefits and applications such as exponential or quadratic speedup over classical algorithms. The image contains an exploration of quantum computing and its promise. As you can see in this slide, the left side, the promise of quantum computing. Quantum exponential speedup is represented as a leap to a much faster computing domain compared to a classical computing. The graph compares computing power over time, showing an exponential rise in power with quantum computing, potentially surpassing classical methods, Moore's law. On the right side, the promise of exponential speedup. Quantum computing is envisioned to break unbreakable crypto systems by enabling faster factorization and problem-solving techniques, provide more accurate weather simulations and predictions, simulate viruses and other complex biological systems for advancements in medicine and research, offer much more in various domains. Very promising. This image hints at a quantum computing offering exponential speedup that could have a far-reaching impact in computing, cryptography, weather predictions, and more. But it also raises the challenge of the unknown aspects of this leap. The image here humorously represents the dream of a cryptanalyst attempting to break the RSA cryptobit system. This is a thought bubble. The cryptanalyst plans to crack the RSA system by finding a super fast factoring algorithm. What's the result? Becoming rich and famous. What's the problem? The task involves factoring an integer n, which is the product of two unknown primes, p and q. Given n equals p product q, the goal is to figure out the primes p and q, thereby factoring n. This is a reference to the RSA crypto system, which relies on the difficulty of factoring large numbers into their prime components. If this problem could be solved efficiently, many modern encryption systems, including RSA, would be compromised. The image connects this difficulty with the allure of becoming a famous codebreaker. On that note, I'm going to pass the floor to my colleague, Dr.